Thanks, Terry. Thank you all for being here tonight to welcome our guest speaker, Dr. Steven Weinberg. Introducing someone who needs no introduction is a fundamental challenge for any vice president of any club. You know, back in college, you were told that you would probably have to do an hour or two of homework for each hour in class. On that basis, I'd like to recommend that for every hour you spend stargazing, you would do yourself a service by reading any of Steven Weinberg's books. In addition to a dozen books, more or less evenly divided into science treatises and reflections on society, he's published nearly 400 articles, including, of course, mostly peer-reviewed contributions to scientific journals, but also 24 opinions in the New York Review of Books. Those of us who live in the hinterlands do not easily perceive how it is that those who make decisions in Davos, Switzerland, form their intentions. But Dr. Weinberg is one of the intellectuals who provides them with clarity. So on that note, and without further ado, please join me in welcoming tonight's guest speaker, Dr. Steven Weinberg.
Oh, thank you very much. I know that everyone here is interested in astronomy, and I hope that many of you are also interested in history. The history of astronomy, I think, is unique among all the sciences in several different ways. For one thing, astronomy became something that we would recognize. There's some kind of squeak. Does anyone know what that squeaking is? Well, all right. Does it sound better now? Michael, how does this sound?
It sounds fine. Sounds fine, Professor. I couldn't respond because we just muted everybody except you.
Oh, I see. Okay.
All right.
For one thing, astronomy became what we would recognize as a science in the modern sense, a natural science, much earlier than the other natural sciences like physics or biology or geology. In fact, many centuries earlier. Look back to the time of the Roman Empire. In physics, what do you have? Well, there was an idea about atoms that was being put forward by the poet Lucretius. And there were supposed to be 4 kinds of atoms: earth, air, fire, and water. Why those in particular? And how do you know matter is composed of atoms? There was no real understanding of any of that. And that, in fact, that really is the kind of question that just wasn't asked. How do you know? Or look back to medicine in the time of the Roman Empire. Again, I don't know, the number 4 seems to have a hold on people's imagination. Illness was supposed to be due to an imbalance among 4 humors: black bile, yellow bile, blood, and phlegm. That theory, humorism, goes back to Galen, a Roman physician, and continued to dominate medicine for centuries without the slightest evidence for it. But when you come to astronomy, you have Claudius Ptolemy. This is about 150 AD, in the time of the Roman Empire, although he was in Alexandria rather than in Rome, working out a theory of the motion of planets against the background of the fixed stars. By planets in those days, of course, the only things that we call planets that they knew about were Mercury, Venus, Mars, Jupiter, and Saturn. They didn't regard the Earth as a planet. But they did regard the sun and moon as planets. So these were bodies moving against the background of fixed stars. Now, there was a theory of how they moved, going back to Aristotle and some of his contemporaries, that the planets are on crystalline spheres which revolve around the Earth. There are various ideas about the order, but certainly the moon was the closest to, did I leave the moon out before? Maybe I did. The moon was the closest to the Earth, and then you had Venus and Mercury and Mars and Jupiter, Saturn. Somewhere in there was the sun. This theory crudely accounted for the ways that the positions of these bodies change relative to the fixed stars, the stars that form the constellations, which always appear in the same place relative to each other. But it didn't really fit it. It was known that there were discrepancies, and Ptolemy, about 150 AD, worked out the implications of the discrepancies, coming to the conclusion that the planets move on epicycles around around a point on the orbit, which then moves around the Earth. Sometimes epicycles on top of epicycles, and so on. Now, you may sneer at this and say, well, that's not real. But in fact, if you take Ptolemy's theory and just change your point of view and say you're going to look at the sky from the point of view of someone riding on the Earth, which Ptolemy thought was in motion. I'm sorry, if you change your point of view from someone riding on the Earth, which Ptolemy thought was not in motion, to someone riding on the sun, Ptolemy's theory is almost exactly the Copernican theory. Together, not just the Copernican theory with planets moving on circles around the sun, including the Earth, but with slight corrections to the circular motion as represented by the epicycles, which were finally understood by Kepler as due to the fact that, in fact, they're not circles, they're ellipses. But the tiny corrections to the circularity of the orbits was already being measured by astronomers in Roman times well enough to make a theory of the apparent motion of the planets against the background of stars, which was as good observationally as anything Copernicus came up with. It was real science. There's another respect in which astronomy was way ahead of the other sciences, and that is that it was useful. Well, it's not surprising. After all, the reason that astronomy was centuries ahead of the other sciences is simply that astronomical phenomena are very simple. Well, not if you're going to look at things like black holes, but if you just look at the night sky and observe the stars and the sun and the moon and the planets, their motion is simple, repetitive, periodic. It's not hard. It's so much simpler than observing a waterfall, let alone a living being. And so it was natural, just because of the nature of the subject matter, that astronomers could understand what they were looking at so much earlier than physicists or biologists. And because of that, it was useful. But I have to say, it was useful before it became scientific. Before there was writing or history, or perhaps even before Homo sapiens, people must have had some idea, looking at the position of the sun in the sky, that if it's just rising That's always more or less the same direction, which we call east, a word which has its root in the word for rising, as in Easter, or setting, that's the west. And you know that the longer it's out in the sky, the hotter it is. All of these, you know that if the sun is at the highest point in the sky, it's about equal time between dawn and sunset. All these things must have been familiar to our ancestors before they could write about them, before there was such a thing as writing. And it wasn't just the sun, but the stars. We know that as early as 3000 BC, the Egyptians were using the times that different stars or constellations rose just before or just after dawn, or set just before or just after dawn. They were using those times to define dates in the year so that they would, for example, expect the Nile to flood when the Pleiades rose just before dawn. The stars were used, of course, for navigation also. So they still are, as a matter of fact. Although I have to say, on a cruise ship, one of the few times in my life I've been on a cruise ship, we went up to the bridge. My wife teaches, among other things, admiralty law, so we use that as an excuse for letting the ship's officers allow us on the bridge. And they were navigating using satellite signals. And I asked them whether they could do celestial navigation, and he looked at me blankly. I don't think he had ever heard of it, the ship's officer who was up there. So maybe that's now a dead art. But until recently, people used the stars. They knew that the Big Dipper was always somewhere to the north. You find that even in Homer. The advent of scientific astronomy, for example, in the work of Ptolemy, didn't really do much to enhance the real usefulness of astronomy. And I put the word real into that sentence because it did a lot to enhance the apparent usefulness. There was a pseudoscience, astrology, that was popular going back to the Babylonians. And Ptolemy, in addition to writing his great work on real astronomy that the Arabs call the Almagest, wrote another book, the Tetrabiblios, on astrology. And it's natural, of course, if by looking at the stars, you can predict whether your king will win a war or whether you will recover from a disease. Isn't that wonderful? Of course, it's all nonsense. But the nonsense has persisted until the present day. We had recently, not that recently, 40 years ago, we had a president's wife who believed in astrology. The foundation of the Republic of India was delayed so that it would occur on an astrologically favorable day. I don't understand how this nonsense can go on century after century, but I think it's a failure of our teaching science, because when you see how science really works, astrology looks childish. Another big difference between astronomy and the other sciences, which is closely related to the first two that I mentioned, is that it became big science, by which I simply mean spending a lot of money, much earlier than the other sciences. And the Greeks, in the successors to Alexander's general Ptolemy, this is a different Ptolemy, this is the Ptolemy who was a general of Alexander, built a museum in Alexandria, part of which was an observatory to look at the heavens. And the tradition of kings supporting observatories continued as long as there were kings. And this, I have to admit, was largely because of astrology. When Baghdad, the capital of the Abbasid Caliphate, was sacked by Ulugh Bey, I think it was 1258, if I remember correctly, one of the first things he did with the riches that he was able to steal was to build a great observatory in Samarkand, back in his home country. And the reason why he thought of building an observatory is because astrologers had encouraged him to besiege Baghdad, and it had worked out very well, and he wanted to be on the right side of astrology. Well, what can you do? The link was not always with astrology, I'm glad to say. The most important, until modern times, great astronomical observatory supported by royal funds was the observatory on the island of Ven in the straits between, well, now it's between Denmark and Sweden. In those days, both sides were Danish. This observatory was built for the use of the Danish nobleman Tycho Brahe by the king at the time, Frederick II. And Brahe was able, using, there were no telescopes yet, this is before Galileo, but Brahe was able to use enormous instruments for measuring angles between planets and stars, anchored into stone foundations deep in the earth, which are, my family and I have been there, and that's the only thing you can see now left from the observatory, of these massive stone foundations to which the instruments were anchored. He was able to measure angles, particularly the planet Mars, which is by far the easiest to observe. He was able to measure the position in the sky against the background of fixed stars of Mars as the year passed, accurately enough so that Kepler, using his data, was able to finally make the great realization that no, there are no epicycles, it's just the planets move on ellipses. The development of, well, that cost a lot of money. In fact, enough money so that when King Frederick II of Denmark died, his successor, Christian IV, who was perhaps Denmark's most popular king, didn't want to spend any more money. Certainly not for noblemen. He was sort of at war with the Danish nobility. And so he just told Brahe that he wouldn't support him anymore. And Brahe left, and he went to, I think he went to Vienna first and then Prague, or it may have been the other way around. But that tradition of spending a lot to learn about the heavens, even for people who are liberated from the fallacies of astrology, continued. Much of it in the 19th century in the hands of independently wealthy people. For example, I think you've all seen pictures of the beautiful spiral arms of galaxies. You can't see those spiral arms with the naked eye. You need a telescope. In fact, you need careful observation with a telescope to see the spiral arms. The first person who saw them was an astronomical amateur, the Earl of Rosse in England, I think. Well, certainly in what is now the United Kingdom. And he built his own telescope, a 40-foot long monster that he called the Leviathan. And with it, he discovered that galaxies have spiral arms. Of course, he didn't know that they were galaxies. He didn't know that they were clusters of stars, of which our own Milky Way is just one example. That wasn't known until the 20th century. But whatever they were, they had spiral arms. Toward the end of the 19th century, millionaires who wanted to safeguard the reputation against the muckrakers of the time put money into large telescopes and observatories. There was Yerkes, the streetcar king of Chicago, who actually you can read about in Theodore Dreiser's trilogy, The Financier, The Genius, and The Titan, although he's given a different name. Yerkes built an observatory on north of Chicago where the sky is dark. And it's still there, I believe. The great astrophysicist Chandrasekhar did much of his work at his desk at the Yerkes Observatory. And then there was Hooker, who funded the 100-inch telescope on Mount Wilson outside of Los Angeles, with which Edwin Hubble, I think in 1922, discovered that there were oscillating there were stars in one of the nebulae. There were stars whose brightness oscillated in a way that had already been identified and correlated with their absolute luminosity by Henrietta Leavitt. And knowing their absolute luminosity and observing their apparent luminosity, Hubble was able to tell how far away this cloud M31 was. And in fact, it was many times further away than the size of our Milky Way, which had already been measured from measurements of the, complicated measurements I won't go into. And so for the first time, we realized that we were not alone in the sense that our Milky Way, which we already knew was a cloud of billions of stars, was not the only one in the universe, but that there were countless other, what we now call galaxies, some of them larger, many of them smaller than our Milky Way. And this has been another theme of astronomy, which is not unique to astronomy, and that is that it's revolutionary. From time after time, astronomers have told us things that disturbed us because they showed that our position in the universe not only does not agree with what the religion of the time taught, but is not particularly special. You can go back to the Greeks, the philosopher Anaxagoras, who lived about the same time as Plato, taught, for reasons I've never been able to learn, that the sun is larger than the Peloponnesus. The Peloponnesus, of course, is the peninsula sticking out south of the mainland of Greece. And for his pains, he was tried by a democratic court. Athens was a democracy, and the good people of Athens exerted their collective wisdom and had him executed for this crime. Later, when the center of Greek scientific thought had moved to Alexandria, about a little after 300 BC, a brilliant mathematician, Aristarchus of Samos, actually set out to use real observations of the sun and the moon, especially during eclipses, to estimate the distance of the sun and moon in units of the size of the Earth. We actually have his book. A lot of Greek astronomy has been lost, but we have the book of Aristarchus of Samos, and his mathematics is impeccable. He had the problem really nailed. Unfortunately, his observations were impossibly bad. He's the real prototype of the brilliant theoretical scientist who's incompetent at observation. At one point, he said the angular size of the sun and moon are about 2 degrees, where in fact it's about a half a degree. But he, even with all his bad observations, he came to the conclusion that the sun is much larger than the Earth. And this time on real scientific grounds, terribly disturbing. In fact, there's some argument that he may even have anticipated Copernicus and concluded from this that it's the sun that's at rest, not the Earth. We don't know that that's true. And in the same way, Hubble, discovering that our Milky Way is just one of billions of what were then called island universes, that was also a bit disturbing, although by then no one was about to hang Hubble, I'm glad to say. Of course, these days you never know. So astronomy has played, this is another kind of usefulness of astronomy. Of course, I don't think any of this compares to the revolutionary character of Darwin's discovery of his explanation of the variety and adaptation of living things in terms of evolution through natural selection. That may have been the most revolutionary of all scientific discoveries, but it's outside the scope of my talk. Astronomy was useful in yet another way, and still is, and that is because of the simplicity of astronomical phenomena. It is in the sky that we learn the laws of physics. Of course, the obvious example of this is Isaac Newton. Newton was asked by his friend Christopher Wren. Wren knew about Kepler's work on elliptical orbits, what kind of what kind of law of force would produce an elliptical orbit. And Newton claimed later he already had the answer before he was asked that question. But one way or another, that is the question he answered in his book, The Mathematical Principles of Natural Philosophy, which I think is universally regarded as the greatest book on physics ever written. Most important, let's say. It's not easy to read. I don't know how Newton could have come to his conclusions about the laws of motion and gravity without the laboratory of the heavens to rely on. But this continues. The fact that atoms come in discrete states, each with a definite energy, and that the reason, well, that was first observed in the early 19th century by Bessel and one other person whose name I forget, who observed that the rainbow of colors, when you let the light from a distant star go through a prism, well, first through a telescope to focus the image of the slit, and then you spread out the colors with a prism and observe them on a screen, you see countless dark lines. Each one of them, it was later realized by Niels Bohr, represents an energy of a particle of light, which is just capable of lifting the atom from one state of definite energy to a higher state of definite energy. The explanation of atomic spectra stands at the very beginning of modern quantum mechanics, which is that's the language in which the laws of physics are written. And we wouldn't know about it without the observation of the spectra of stars. On a more trivial level, there are elements that we wouldn't know about if we hadn't seen their spectra in stars. Like there's one who was first discovered in the late 19th century by Norman Lockyer, that was first discovered in the sun, and was therefore called helium. Now, in one sense, I mentioned the fact that astronomy was big science in the sense of costing a lot of money long before physics. And well, look at the comparison between Hubble on Mount Wilson using a 100-inch telescope, cost millions of dollars, and in those days, $1 million was real money. And Lord Rutherford in England discovering the nucleus of the atom with an experiment funded by the Royal Society at a level of 70 pounds sterling. Physics did not become a big science until at Berkeley, physicists started to build accelerators that could produce beams of particles with known definite energy and direction that could be used to break into atomic nuclei, see what's going on there. And so I remember I was a professor at Berkeley in the late 50s and early 60s. Berkeley was the first place where this kind of big physics was done. They had an accelerator which was large enough to get enough energy to produce antimatter for the first time, antiprotons to be specific. But it fit into a building. It was a big building up high on the Berkeley Hills. And the physicists at Berkeley knew that to make the next step in learning the laws of physics, they had to go to a much larger accelerator. And the tragedy for them was that it would have to be too large to fit in the Berkeley Hills. And indeed, it was built in the prairie outside Chicago, its present-day Fermilab. these instruments for physics became not things you find in physics buildings, but they became features of the landscape. As physics became big science, increasingly so after World War II, astronomy did too. Not only were large telescopes built, finally, I think it was in 1952, the Hale 200-inch telescope went into action on Palomar Mountain, but it became clear that there were things that could not be observed from the Earth's surface because what you're trying to observe, the radiation just doesn't get through the Earth's atmosphere. And so it was necessary, for instance, infrared radiation won't get through the Earth's atmosphere. And so it was necessary to put observatories in orbit, which gets really expensive. There is a glow of microwave radiation left over from 13.8 billion years ago that could only be, well, that was in fact discovered from the ground with a very large radio telescope owned by Bell Labs, but could not be studied in detail without getting out into space. And in fact, much of our knowledge of the early universe comes from observations made with a microwave observatory at a position called L2, which some of you know is about 4 times farther away from the Earth than the Moon, on the opposite side from the sun. So it's a nice, quiet, cold, dark place. And the new big telescope, largely an infrared telescope, the James Webb Telescope, will also be put out at L2. And we have seen here, even here on Earth, the National Science Foundation, which normally doesn't support large facilities, finally put its money where its mouth is and supported the construction of a laser interferometric gravitational wave observatory. In fact, 2 of them, one in Louisiana and one in Washington State, which discovered, as I spoke about the last time I spoke to your group, gravitational waves coming from the coalescence of black holes and more recently neutron stars, many billions of light years away. So science, whether it's astronomy or physics, has joined together to become very big, very expensive. And I want to just close by saying this isn't because of some kind of egotism or science imperialism on the part of physicists and astronomers. When you've measured everything you can with in the basement of a physics building, you have to get outside. You may get out into the Illinois prairie, or you may get above the Earth's atmosphere. But it is not given to us to learn what governs the universe simply by observing the things around us, the things that are easy to see. So we do what we have to. And it's just wonderful how it works. You know, these experiments suggest new theories, or the theories suggest results of experiments, and they get together. They often turn out to agree with each other. I've seen that many times in my lifetime. It is enormously rewarding and exciting, and we can only hope that the governments of the earth will be willing to go on supporting it. And one practical suggestion I can make that might help in that direction is to stop supporting manned spaceflight, which has no scientific value except to determine the effects of spaceflight on people, which is not, to my mind, a question that in itself should drive our research. Manned spaceflight is very exciting. It's a wonderful spectator sport. You know, I really enjoyed that movie, Apollo 13. It's exciting as hell, but it has no, and if you, it may have been worthwhile pursuing in the 1960s because we were in some kind of prestige race with the Soviet Union. But those days are really gone. And it costs so much money that could be spent on what I think is really important, which is through the work of physics and astronomy and all the other sciences, the life sciences, and so on, to discover the rules that govern the world. And as you can see here, to explain the world. Thank you very much. I'm happy to take questions if there are a few.
Thank you, Dr. Weinberg. That was great. Anybody that we don't raise hands here, so just unmute yourself if you have a question to lead off with.
I'm going to put this on speaker view so I can see who's speaking.
Dr. Weinberg, clearly you are currently obviously working on the history of science, and I was just wondering if you're focusing on any other particular areas at this time.
No, I'm not. I'm writing a little bit about the history of my own time, but nothing that I'm not writing any books for publication. My latest book is an advanced undergraduate treatise called Foundations of Modern Physics, which is a historically oriented but quite technical introduction to modern physics, starting with atoms and the properties of gases and so on, going through thermodynamics, kinetic theory, and then into early quantum theory, relativity, quantum mechanics, a little taste of nuclear physics, a little taste of quantum field theory. It's all in a historical framework, but the point is not to teach history, the point is to teach the physics. I'm not a historian.
Okay, thank you.
What do you think is the single greatest discovery in your lifetime?
Oh, in my lifetime? Let me think. Oh dear, that's hard to say. There are things that were discovered, but they were pretty well anticipated. And there was a lot of hoopla about them, but in a way I don't know when the discovery, I think the discovery of the cosmic microwave radiation background in 1965 by two radio astronomers working at Bell Labs, Arno Penzias and Robert Wilson. The reason that was so important, it had in a sense been anticipated. There had been work decades earlier by George Gamow and two of his collaborators who actually went farther than he did Ralph Alpher and, oh God, he's going to kill me if I don't remember his name. Sorry, he was here too at UT. Oh, well. What they predicted that since the universe is expanding, it was once much more condensed and hot, and some of that radiation will be left over, and you can sort of guess what the temperature of the radiation would be from the present ratio of the number of photons, particles of light, to atoms. And in that way, they made a rough guess of about 5 degrees above absolute zero. And they talked to some radio astronomers who said, oh, you never measure that. 5 degrees. I mean, imagine pointing a radio antenna at a body which is cooled to just 5 degrees above absolute zero and trying to detect the radio waves from it, just due to the motion of electrons, other particles inside it. It's not easy. And so they gave up. And then in 1965, this pair of radio astronomers tried to get all the static, all the noise out of a large. Anyway, the important thing, while I look up the names, is that not just that this had been predicted and now is being measured, but that for the first time it forced us to realize that there was such a thing as an early universe, that the universe started out very different from what we have now. And it began a huge amount of theoretical and experimental work. Like I mentioned, the radio telescope at L2, which is there just to study this radiation. We now think we really understand the first second of the expansion of the universe. Before 1965, I got a little interested in cosmology, but it seemed intellectually disreputable. All speculation and people just stating their views without any real basis, just like a religion. And whereas after 1965, it became normal science. By normal science, I don't mean that we knew everything we wanted to know, and in fact, we still had some wrong ideas, but it was respectable to write papers about what kind of measurements could be done, or what we learned from this measurement or that measurement, or what kind of theory might be relevant in the early universe. I was enormously turned on by that discovery. I think that was the greatest discovery, at least in the physical sciences of the 20th century. Thank you for giving me a chance to go down memory lane.
Thank you.
Professor, you're an advocate for strong realism. In your book, To Explain the World, the underlying theme is that science was discovered and not invented. Would you speak to that point?
Well, there are various ways of trying to learn about things. You can examine the entrails of birds, or you can write down your dreams when you wake up. People have tried those over the centuries. It wasn't obvious how you would explain the world. Gradually, however, particularly, I would say, starting with the study of astronomy in Hellenistic Alexandria, a way of approaching nature appeared, involving observation and mathematics and so on. Aristotle was very good at using observation. He knew, for instance, that sound traveled at a finite speed, much less than the speed of light, which he thought was infinite, from observations of the fact that he would hear things from a distance after he saw them. He knew that the Earth was round because of the appearance of the sky changing for travelers as they went north-south. But he never thought of using mathematics in this context. Somehow we stumbled into this method of learning about the world, which works. And because that's the way the world is. The world is governed by laws that, at least in the forms that we're capable of discovering them, are mathematical, are impersonal. There's nothing about the king's illness in the positions of the stars. Nature is impersonal and governed by mathematical laws. That's the way nature is. And so we discovered how to learn about that because it wasn't obvious at all. Those people like Aristotle were very smart, but they didn't know how to learn about nature the way we finally learned how to do it. I made the analogy in the preface of my book with agriculture. Agriculture, of course, started with human beings in Neolithic times. They realized that if you put seeds of wheat or chickpeas or various things like that into the ground, they will, in a few months, you'll have a harvest. They didn't know what they were doing, but it worked because what they were doing was sufficiently in tune with the realities of biology so that you could actually grow food that way. And they stumbled into the discovery of agriculture just as we stumbled into the discovery of science. They did invent agriculture in a sense because, of course, without them, there wouldn't have been any agriculture. No farmers, no farms. But it was there waiting to be discovered because that's the way life works. You put the seeds in the ground, you water them, and look what you get. And I think it's in the same sense that we discovered science.
Hi, my name is David. Is there any evidence that ancient Greece or ancient Rome used a telescope to look at stars or the moon?
I don't think so. I have heard something, someone used some speculation about a crystal. They didn't have good glass. They didn't have window glass in the ancient world. They had glass, but it was faience used for jewelry, cloudy, and you couldn't make a telescope with it. They may have possibly, I think I've read somewhere about speculations that someone used a crystal. But if they did, it was lost. I mean, it played no role in the history of astronomy. We haven't learned, nothing that was learned from it has stuck with us, put it that way. If it happens at all.
Okay, thank you.
Of course, they knew about mirrors.
Professor Weinberg, one more question, please.
Yeah, all right. Just let me add that they did know about mirrors, and I suppose they could have, even not having glass, they could have made a Newtonian telescope, a refractor instead of a reflector. I'm pretty sure nobody thought of that. Yes. One more question, then I go to bed.
Astronomy is a great example of both of our major theories of physics, both general relativity and, of course, quantum mechanics. You talked about spectral lines. You talked about all the great things that we've observed in gravitation. Yet we don't have a unified theory of quantum mechanics and gravitation. Do you have a preferred or what you would bet on as a preferred model that's going to emerge in the next 50 years for us in terms of unifying these two theories?
We actually do have a unified theory of gravitation and of gravitation and quantum mechanics. That is, we can treat gravitational phenomena by the methods of quantum mechanics under the assumption that we're looking at energies per particle that are very small compared to the fundamental length scale called the Planck scale, at which gravity becomes a strong force. You can ask yourself, what mass would the electron have to have so that the gravitational attraction of two electrons equaled its electrostatic repulsion? The answer is it's a mass called the Planck mass. It's about a 1 with 18 zeros times larger than the mass of a hydrogen atom. We don't do experiments with energies like that. I mean, we do experiments with energies maybe a 1 and 13 zeros larger. No, I'm sorry, what I'm saying is wrong. With about 4 or 5 zeros larger than the mass of a hydrogen atom. We're never in the foreseeable future, by any method that anyone can imagine, going to do experiments at the Planck scale. But let me go back to my answer to your question. As long as you're looking at energies that are much less than the Planck scale, which we inevitably are, you can combine quantum mechanics and relativity and calculate the answer to any question you might want to ask as a series in powers of the energy divided by the Planck scale, a very tiny number for any energy that we can study. So it's a very good approximation, and it works, and it doesn't lead to any fundamental philosophical problems. It does lead to infinities, but the infinities all cancel. This is what's called effective field theory, and it's something which I played a role in bringing into being. The problem is that if you expand in powers of energy divided by the Planck mass, when you get up to energies of the order of the Planck mass, you're looking at powers of 1. And 1 square is 1, 1 cube is 1. You can't do any calculation. There's no method of calculation that works. So we have a theory that works at low energy, but which loses all predictive power when you get up to sufficiently high energy. And the question then is, what takes over? What is the correct theory that doesn't break down at very high energy? Some people think it's string theory. Some people think it's a kind of theory called asymptotically safe. My bet would be on string theory, but we don't know. We don't have a satisfactory theory for that. So you're right basically you're right in what you assumed.
Thank you.
Oh, well, thank you for your good questions, and thank you for your attention. Have a good rest of the evening.
Thank you,
Goodbye.
Dr. Weinberg. We really appreciate your taking the time to speak to us.
Signing off.
Much. Yay. Thank you.
Yay.
Thank you.